Okay, so I want to start by fixing something I had in the first lecture. There's really different books use different notations, and I forgot which notation this book uses. But we're first going to define something called the Heaviside function. That is a function that has a jump of a particular kind in it. So it's the function uc of t. And I defined this last time, but I defined it backwards. I made it 1 jumping down to 0. This book uses it the other way. It's 0 if t is strictly less than c. And it's t, if t is greater than or equal to c, it's 1. And actually, you could do it where you don't have to specify the value of u at t. It could be anything. But I believe this is the way Boyce and DePrima does it. So we'll stick with it this way. So remember, if you have the, so let's graph that. If if t is less than c, the function is 0. So it's 0 all over here with an open circle here. And then at 1, at t equals c, it jumps up to 1. Okay. All right, so you can think of this, and what I graphed last time and called u of c is actually 1 minus u of c, uc of t, because that one would be 1 minus 0 when t is less than c, so that would be 1 all the way up to c. And then it would be 1 minus 1, which is 0, when t is greater than or equal to c. Okay. So that's what I called last time I really graphed 1 minus. So this is what we're going to call the Heaviside function u sub c. And so you can think of this as an impulse function that when you see when the value of the function is 1, whatever you're studying is switched on, and when the value of the function is 0, whatever you're studying is switched off. So say if you have a forcing function, when t is in this range, the force is not working. As soon as t gets greater than or equal to c, it's on. So it takes the value 1. So you can do this in circuits or vibrations or mechanical systems and so on. So let's practice a little bit with this function. You can write lots of kind of step-looking functions. You can write most of them by writing something involving these functions or multiples or sums or differences of these functions. So suppose I define h to be u5 of t minus u10 of t. Now, what does that look like? What does the graph of that function look like? Well, the first one is 0 if t is less than 5, and it's 1 if t is greater than or equal to 5, minus the function that is 0 if t is less than 10, and it's 1 if t is greater than or equal to 10. Okay, so now we just got to be careful. So when t is strictly less than 5, this one's 0 and that one's 0. So it's definitely 0 if t is less than 5. What about if t equals 5? If t equals 5, this one becomes 1 and it stays 1 forever after that. But this second function is still 0 until you hit 10. So from t between 5 and 10, it's 1 minus 0, so it's 1. And then once t gets bigger than or equal to 10, this function stays 1. The first one is 1. The second one is 1. 1 minus 1 is 0. So if you graph this, it would look like the function that is 0 until you get to 5, an open circle at 5. Between 5 and 10, it's equal to 1, close at 5, open at 10. And once you hit 10 and forevermore after that, it becomes 0. So that's really a step function. It steps up and then it steps down, okay? All right, so we are going to study ordinary differential equations with impulses as the forcing function. So that'll be as a discontinuous term. I mean as the inhomogeneous term. So we're going to we're going to study this using Laplace transforms. And so to do this, let's look at what is the Laplace transform of something like UC of t. Okay, so we're going to calculate that. So by definition, that's the integral from 0 to infinity of UC of t e to the minus st dt. Okay. Now, UC is 0 until t equals c. So in other words, from 0 to c, this is 0. And then from c to infinity, UC of t becomes 1. So it's e to the minus st dt. So this is 0. When you integrate this, you get, when you integrate this one, you get e to the minus st divided by minus s, evaluated from infinity to 0. As t goes to infinity, this goes to 0 as long as s is bigger than 0. And then you subtract the value at 0. So that's e to the 0 over minus s, and I'm subtracting it, so that's 1 over s. So the Laplace transform of this guy is equal to 1 over s. Okay, and you'll find that in your Laplace transform table, and that's for s greater than 0. And you'll find that in your Laplace transform table, and that's exactly why. Okay. All right. You can use this Heaviside function to shift a function to the right or to the left, depending upon which way you want to shift it. So, for example, suppose I have some general looking function. Let me draw something that I can duplicate easily. Suppose this looks like this is f of 0 right here, and this is y equals f of t. Okay. And now if I look at the function uc of t times f of t minus c, all right, when you change the argument of the function from f to f minus when you change the argument of a function from f to say that again. When you change the argument of a function from t to t minus c, that means you shift the graph of the function to the right, c units. So this one would shift this graph over c units. So what used to be f of 0 is now, and started at 0, moves to it still has the same value that it did over there, but now it's moved over. And so if I drew this perfectly, that would look like the exact same function just slid over c units. But because I multiply by uc of t, it's 1 when t is greater than or equal to c, so that gives me this piece. But when t is strictly less than c, it gives me 0. So here's what multiplying by uc of t and then shifting the argument does to a function. All right, why is that important? Well, let me give quote stated as the following theorem. Suppose that capital F is the Laplace transform of little f for all s, maybe s is in a range, and for all a, for all s, let me say greater than or equal to a greater than 0. Okay, then for c greater than 0, the Laplace transform of uc of t, f of t minus c is e to the minus s times c times the Laplace transform of little f. So shifting the function to the right and then making it 0 to the left of c, which is what this function does. We call this y tilde. That's the shifted version. Okay. So taking the Laplace transform of the shifted version To do that, all you have to do is take the Laplace transform of what was the original function, little f, because that's what capital F is. It's the Laplace transform of the original function, little f, and you multiply by e to the minus sc, where c is the amount you shifted that function over. All right, let's see why that's true, because that looks a little magical and it's not hard to prove. So if you look at ut of c times f of t minus c, okay, by definition, that's the integral from 0 to infinity, uc of t, f of t minus c, e to the minus st dt. Okay. All right. And uc is 0 for t less than c. So really, there's nothing in that integral is the integrand is 0 until you hit c. So I can just start the integral from c. Then it's f of t minus c, because u is 1 once t is between c and infinity. Whoops. Times e to the minus st dt. Okay. All right. And you sit there and you look at that for a minute and you say, okay, I'm going to make a change of variables. Let tau be t minus c. Then d tau is equal to dt. And notice then that, that t is equal to tau plus c. So this thing is equal to the integral from c to infinity. Whoops, let me be careful. Let's be careful. We got to change the limits. Now, when t is equal to c, the lower limit, then tau is equal to 0, because I'm going to change to an integral with respect to tau. And as t goes to infinity, tau will go to infinity. That's what this tells you. And then this is going to be f of tau, and then e to the minus s. T is tau plus c. And then dt is the same as d tau. Okay, so this is the integral from 0 to infinity of f of tau e to the minus s tau times e to the minus sc d tau. But this thing doesn't have anything to do with the variable of integration. So I can move it on out to the front. So this becomes e to the minus sc times the integral from 0 to infinity of f of tau e to the minus s tau d tau, which is the definition of the Laplace transform of f. We just called the dummy variable tau instead of t. So this is e to the minus st times f of s. Okay, the Laplace transform of little f. Okay, so that proves it. That proves the theorem. But this is an important formula that'll be useful both for taking the Laplace transform and when you have to invert it. Because remember, every time you get a formula for the Laplace transform, you get a corresponding formula for the inverse. This also tells us that the inverse Laplace transform of e to the minus sc times f of s is uc of t times f of t minus c. So if you have an exponential term times the Laplace transform is something you know, when you invert the Laplace transform, you get whichever function this capital F came from is shifted c units, and then because of this, it's pre-multiplied by the heaviest side function at c. Okay. All right, so let's do a couple of examples. So an example, let's start with f of t is, let's say, sine t if t is between 0 and pi over 4. Let's scratch out the equality there. And if t is bigger than or equal to pi over 4, then let's make it be sine t plus cosine, I'm running out of room, t minus pi over 4. Okay, so that's an if. Okay. All righty. So let's find the Laplace transform of this function. Okay. So how do I want to do that? That's a little bit tricky, but notice that there's a sine t in both places. But then when t is bigger than pi over 4, you have to add on this cosine term. So let's let g of t be the function that is 0 if t is less than pi over 4, and have it be cosine of t minus pi over 4 if t is bigger than or equal to pi over 4. Okay. Then f of t could be written as sine t plus g of t, right? So that means it is sine t. But how would you write this function? Notice that's a Heaviside function. It has the jump at pi over 4. That's u pi over 4t. And then it gets multiplied times cosine t pi minus pi over 4. How do you know this and how do you get used to it? By practicing, by looking at these things long enough to see how do you write it, how do you shift it, what's going on. That's why you have lots of homework problems on this, because it does take practice. It's not something you see right away. Okay, so now we have that. So now let's try to compute. Now we have f written in a way where we can use the Laplace transform tables. Because now when you go to compute the Laplace transform of f, the Laplace transform's linear. So it's the Laplace transform of sine t plus the Laplace transform of the Heaviside function, u pi over 4t, times cosine t minus pi over 4. Okay. And when you look up this one on the table, that will tell you that is 1 over s squared plus 1. So that's from the table of Laplace transforms. You look up sine t on the right-hand side, it'll tell you this on the left. This you don't find on the chart. What you do find on the chart is u sub c of t, f of t. Okay, and so what does it tell you? That is the Laplace transform theorem that we just had. Says if you have u sub t of f of t minus c, then the Laplace transform of that is e to the minus s times c, but our c here is pi over 4. And now you have to take the Laplace transform of cosine, as if it just was cosine t. And when you look at the Laplace transform of that on the chart, you'll get s over s squared plus 1. Okay. So again, this is just using the chart, but the chart is not so trivial to use. You really have to know what you're doing and be careful with it. Okay. So that's the Laplace transform of the original function we started with. All right. Let's try another example. Suppose I'm given that the Laplace transform of my function is 1 minus e to the minus 2s over s squared. And I ask you to find little f of t. So the inverse Laplace transform of that guy. Okay. So I want the inverse Laplace transform of capital F of s. That is little f of t. Okay. All right. So I'm going to break this one into two pieces. So that's going to be the inverse Laplace transform of 1 over s squared minus the inverse Laplace transform of, square that bracket, e to the minus 2s over s squared. Okay. Now, when you look up 1 over s squared, now when you look up to invert the Laplace transform, you look at the right-hand column. when you find 1 over s squared in the right-hand column and you look back to the left, you will find that the function that came from the inverse Laplace transform, in other words, of 1 over s squared, is just t. This you don't find exactly like that, but what you do find is something in the chart in the left-hand side that says e to the minus s times, basically, let me not call it f, because f means something here already, times g of s. So how do you invert the Laplace transform of that? When you look that up on the chart, it'll tell you u sub c of t times g of t minus c. So what's our function here? The g of s is 1 over s squared. Which function has that as its Laplace transform? We just saw that. It's t. And you're multiplying it by e to the minus 2s. So this will be u sub 2, because c is 2 here in this formula. So this, I'm sorry, c is c is 2. So that's u sub 2 of t. 1 over s squared goes with t, but you have to shift t by c. So this is t minus 2. Okay. So it's a little bit tricky. So what is that function? All right, so this was just a little side calculation. So f of t, what is that? So this is the function this is t minus, again, I'll remind you, this is u sub 2 of t is 0 if t is less than 2. And if t is bigger than or equal to 2, it's 1. So this becomes t minus 2. So what is the f finally? It's that's t minus 0 if t is less than 2. And if t is greater than or equal to 2, it's t minus t plus 2. So that's 2. Okay. Okay. All righty. Okay. So let's do another example. Oops, okay. I'm sorry, mixing up my pages here of notes. Okay, no, let's do a theorem here. All right, so here's another theorem about the Laplace transform. So suppose that capital F is the Laplace transform of little f. For s greater than or equal to s strictly greater than a strictly greater than 0, greater than or equal to 0. A could be 0. And let c be a real number. Okay. Then the theorem is that the Laplace transform of e to the ct times f of t is the original Laplace transform of little f shifted c units to the right. Okay, so in the last theorem, our Laplace transform was multiplied by an exponential. Here, the function you are going to take the Laplace transform of is multiplied by an exponential. So what that does is it shifts the argument of the Laplace transform c units to the right. And again, every time you write a statement about Laplace transforms, you get a statement about the inverse Laplace transform. So the inverse Laplace transform of a Laplace transform shifted c units to the right is e to the ct times f, where little f is the function that goes with the Laplace transform capital F you would give it. And again, why would this be true? You just calculate. Everything can really be done back to the definition. Okay, so when we do this, this is the integral from 0 to infinity of e to the ct f of t times e to the minus st dt. So this is the integral from 0 to infinity f of t e to the minus s minus c times t dt. Okay. And so what is this? This is, think of that as s tilde. That is not the variable of integration. So there's nothing to change in the dt. So this is the Laplace transform of f at the argument s tilde, but what was s tilde? S tilde was s minus c. Okay, so that's it. All right, so let's practice using that one in an example. Okay, so suppose I take suppose G, capital G of s is 1 over s squared minus 4s plus 5. Okay. And now I ask you to find g of t, which is going to be the inverse Laplace transform of capital G. Okay. So little g of t is the inverse Laplace transform of capital G. Okay, so I want to invert 1 over s squared minus 4s plus 5. Okay, if you look that up in the table, there's nothing close to it. So you're going to have to do some algebra to get it into a form where you can use it. So we did something similar to this today. Let me just look at that term we want to rewrite. So what I'm going to do is I'm going to write this as, I'm going to complete the square in s. I'll do this in a slightly different way than I did it today. So I'm going to complete the square in s so I can get something squared plus a constant. So if I complete the square in s, when I do that, I'll get half the coefficient of s, that'll be minus 2. I square it, that'll be a plus 4. So if I use a plus 4 here, I have to add a minus 4 there to balance it out. That's other equivalent ways to think of it. So this becomes 1 over s minus 2 quantity squared plus 1. Okay. And now if you look in the chart, if you look in the Laplace transform table, let me write in a different color. So, hold on. So I'll do my chart calculations in a different color. So in a chart, you would look up and you would see something there for 1 over s squared plus 1. Not s minus this, but 1 over s squared plus 1. And so when this would tell you that came from sine t, sine t. Okay. But since this is shifted, the argument's not just s, but it's s minus 2. So that's this theorem. We have the Laplace transform, or we're taking the inverse Laplace transform of s minus 2 quantity squared plus 1. So that looks like this, but instead of s, it's s minus 2. So then the theorem says you find the Laplace transform that was the basis, that is the s squared plus, this is basically an argument squared plus 1. That goes with sine t. So this theorem says that the inverse Laplace transform, oh, sorry, I was writing that, it wasn't visible. So sorry about that. So let me give you a second to look at that. So the inverse Laplace transform of this s squared minus 4s plus 5 is going to be, according to this, because of this shifted argument, it's going to be e to the 2t, because the c is the thing you shifted it by, that's positive. It's s minus 2, so that's a c, the c is equal to 2. So that's going to give me an e to the 2t times the function which is the inverse Laplace transform of s squared, 1 over s squared plus 1, and that is sine t. Okay. So it's just a little tricky to get used to using the chart properly, but that's an example of how to do it. Okay, so basically that's what you learn in section 6.3, how to do all these things. In section 6.4, you actually start to use them in differential equations.